Okay, so my goal today is pages 4 through 7. That's my minimum if we can. I think there's one on page 9, but at minimum, I want to get through the first tippers problem on page 7. And so this top of page 4 is not really a cookie cutter textbook type of problem. It's just, hey, here's a bunch of works. Now go find the change in energies. It's really just a matter of, do you know how to use different works to find the different changes of energy? And ABC is really going to focus on those versions of the work energy theorem. And so let's go through especially the first 3 changes in energy. Well, we only study mechanics. And so the implication here is it's a change in mechanical. What kind of work do we care about? Work done by who changes mechanical energy? It was that third version of the work energy theorem. So back on the front page, I said you either got to memorize them because they're not on the formula chart. And so changes in mechanical energy happen because of? Come on. Yes, but what kind of work? Non-conservative. Okay. And so on part A, we are just going to care about non-conservative work. Well, they don't identify the works above as being conservative or non-conservative, so we need to. So we're not really making a list like last time, but we do need to identify which force is conservative, which is not. So what about that push work? The work done by a push force, conservative or not? Non-conservative. What about tension? Non-conservative. What about friction? Non-conservative. And then we have gravity, which is a conservative. And we've got a spring, or sometimes you see it as elastic. That would be considered conservative. And just a friendly reminder, these two relate to a potential energy, okay? We don't have a tension potential energy. We don't have an applied potential energy, right? And so that's the quick way of remembering who's what. And so to answer part A, we need to sum up, so kind of sigma, but we're summing all the non-conservative works. And so I'd have a positive 500 plus a negative or minus 800 minus 100, which gives us a negative 400 joules. So that's the answer to A. And by the way, I'm not going to try and make up a problem that has an applied, has a tension, has friction, has gravity, and a spring. Okay, it's kind of extreme. I can't even like quickly think of a scenario that would have all 5. Okay, and so it's just here it is, lay it out there. Do you know how to use the theorems? What about changes in kinetic? Think back to our 3 versions of the work energy theorem. What kind of work gives us a change in kinetic? Network. And so network means we add everybody up. Now I'm going to do this one a little bit different. I could write down 5 numbers. We already summed the non-conservative. So isn't this a true statement? The non-conservative work plus the conservative work? It's just another way. Instead of adding all 5, we still are adding all 5, but we're grouping them into the 2 groups. And so we already found negative 400. Now we just need to add in the 2 conservatives. And if you look up above, the 2 conservatives have a sum of 500. And so our final answer for network and changing KE would be positive 100. So whatever the example is, It's speeding up. Positive change in kinetic, right? And then C, D, and E all talk about changes in U. And so if we kind of lump them together, changes in potential energy equal what kind of work? Conservative, and this one is the one, don't forget the negative sign, okay? Don't forget the negative sign. And so we've already said we have two conservative works up above. We already put them together. And so that negative is part of the equation. And then we would have 500 joules. And then when we break it down into just gravitation, well, now we just care about the negative work of gravity. So it would be a negative 300. So these two, D and E, shouldn't, it's the same procedure as part C. You're just looking at one at a time. And then the negative work of a spring, and they tell us it would be 200. So the change in potential would be negative 200. And then the last one, we actually get to use one of our new equations, change in height. This can also be delta Y. I try to use both, 50-50, so that we're used to both. But it's the same thing. So which energy change do we want to look at for changes in height? Which potential? Gravitational potential. And so that gravitational potential energy change equals that mg delta y or delta h. And so we know that the change in energy is that negative 300. Mass was given in the prompt. They squeezed it in there. 2 kilograms. The gravitational field, we'll use 10. You can use 9.8 if you want. And then solve for your delta y, delta h. And we get what? A negative 15. So what does that negative mean? Is it going ground up or is it coming towards the ground? Towards the ground. The height is decreasing, right? That's what a negative change means. Final height is a smaller number than the initial height. Good on that. It's just to reiterate the 3 theorems, 3 versions of the work energy theorem. Okay, next question is more of your textbook standard. I'm going to call these mid-level, okay? And so number 2 says we've got a 1,150 W motor. What did they just give us? Is it 1,000 weight? Is it 1,000 work? Or is it 1,000 watt? It's watts, which is the unit of. It's joules per second equivalent, but what variable, what physics term is it the unit of? Power. Did y'all read my Harry Potter meme at the beginning? Okay. I had to, right? I can't not put it in there, but I didn't make it. I stole it from Facebook. Anyway, borrowed it from Facebook. Okay. So they give us the power of this motor, and it's going to be used to pull a 150 kilogram treasure chest. So they gave us the mass, and it's going up from the ocean floor at a constant speed. And then it tells us the water applies a resistive force of 800 newtons. Okay, that's different than 800 joules, just saying. Okay, don't mix up the work done by the water and the force of the water. 2 questions. How far can the treasure chest be lifted in 1 minute? How do we feel about 1 minute? 60 seconds is probably a wiser choice, right? I take the approach, I like to start everybody in SI units. That way everybody ends in SI units, okay? And then B, what is the change in energy? Again, AP Physics 1, we just care about mechanical energy for the treasure chest. Well, we're going to answer both, but maybe a good place to start here is what? Step 1, force diagram. Our object is not the water, it's that treasure chest. It's being lifted. If you want to put force of the motor, or maybe there's a cable and you're going to call it tension. Okay, so the subscript may vary a little bit, but I'm just going with lift because it mentions lifting in the problem. What other forces are acting on the treasure chest? The every time force? Gravity. How big do I draw it? Okay, so equal to that lift force. Or is it? Isn't there one more force? There's a water resistant. And actually, before we draw that, what direction is this object going? It's moving upwards. So to resist, the water force needs to be downwards. And you were right that constant speed means my net force needs to be 0. So I'm going to erase gravity. Let me ask you that again. How big do I draw the gravitational force compared to the lift force? It should be smaller, not necessarily half, okay? But in terms of general magnitude, it should be smaller than the lift force because there's a second down force. And we're going to label it, drag, resistance, or FW, F water. That's going to be my choice today. But if you want to call it drag, that's fine. And so with that net force equaling 0, we know that the lift force is going to balance the sum of the gravitational force and the water force. And if they net force 0, let's talk work. What's the net work equal? It'd be 0 as well, right? Because if you have a constant speed, what's your change in kinetic energy? None. You have no change if you have a constant speed. And so what does that mean about the work that everybody's doing? The lift force is doing what kind of work? Positive, negative, or 0? The lift force is up, it's moving up, so it would be doing a positive work. What about gravity? Gravity's doing what kind of work? Negative. And what about the water? Negative as well. And by the way, most of that we just did comes from the 2 little words, constant speed. It tells us good old forces got to balance out. And now it tells us the works have to balance out. So similar to the force statement, we could say that if net work equals 0, the work of the lift has to equal the work done by gravity plus the work done by water. You basically make your net work statement and then move things around since it equals 0. Everybody good with kind of getting into what's happening here? Okay. Now let's go answer part A. How far can the treasure chest be lifted? What are we solving for here? How far we're solving for? Distance. And we already converted our 1 minute to 60 seconds, so we know time's going to be involved. And let's see, there's not time in the work equations. There's not time in the energy equations. What equation are we going to start this with? Joules per second. How about power? What's our equation for power? Technically, there's two equations that we can use. Work over time. And what can we plug in for work? And by the way, which work are we looking at? The power of the motor is doing the lift. So this would be the work due to the lift. Okay. But we're trying to solve for distance. So where's distance going to come into play? Well, work is equal to force times distance, right? And so there's the D that we'll be solving for. Okay. Now, whether I keep plugging in, just knowing myself and knowing that, man, I don't know if I'm going to have room to do everything. I'm going to solve for the lift force over at the equation we already wrote down on the right-hand side. We already said that the lift force was equal to the weight plus the resistive water force. And so they don't give me Fg, but what can we plug in for Fg? If they give you the mass, how do you find the weight? Mass times gravity. So it's that 150 times 10, so that's our mg, plus the water, yeah, it's resistive. Yeah, we said originally it can be negative, but we've already moved it to the other side. So I'm going to keep that 800 magnitude. And what's 1,500 plus 800? 15 plus 8? 2,300. That's newtons. We have not done joules. That's newtons. And that's our lift force. Everybody good? So now I can take that lift force and take the time and the power given, and we can solve for the distance. And so over here, power is equal to that 1150 equals the 2,300 times distance over 60. So you can simplify if you want, do your multiplication, your division. Let me know what you get for distance. 30. Sounds familiar. So we're going to lift this in 30 meters in 60 seconds. What if they said, what's the speed? Since it's a constant speed, it would be half a meter per second, right? 30 meters divided by 60 seconds. They don't ask it today, right? But you could find it at that point. B says, what is the change in mechanical energy for the treasure chest? Now, there's a couple ways to do this. I'm going to keep with the work energy theorem. And so what kind of work equals a change in mechanical energy? Non-conservative. Now, we have not yet addressed which of these forces is conservative or not. You don't have to make a table. Just let's go over to our diagram. Lift force would be conservative or non-conservative? Non. What about gravitational force? Conservative. And what about the force of water, the resistive water force? Non-conservative, okay? So to get the works of your non-conservative forces, just add them up. So the work done by the lift plus the work done by the water. And if you want to at this point, at some point you'll have to, but we know the water is going to do negative work. We already made that decision. And so it's like plus a negative, right? And so if we do these two, then that will be solving for the change in mechanical energy. And so the work of the lift, well, we know the force of the lift, and now we know the distance. And so we can say force lift times distance, and then minus the force of the water times that same distance. We don't have to, but could you factor out the distance since it's the same? Yeah. every moment we lift it, the water's resisting. And so one last step, doesn't have to be, but you could. And we'd get 30 times 2,300. We already found the lift force. And then they give us the water force. And so let me know what you get for, and it's a big number if I remember correctly, the change in mechanical energy would equal what? 45,000. That's okay. It's in joules. By the way, a textbook may report the answer as 45 kilojoules, right? A bigger unit for a smaller number. But that's going to be our final answer. Now, I don't know if you caught on, but to get that 2,300, we added 800, right? Originally, we had to add in the 800 to the weight, and then we just subtracted it. So this is like the same thing if we just looked at gravity alone. Well, how can that be? Gravity is not non-conservative. Watch this. It's unique to this problem. Remember how we said net work was equal to 0? Remember how we said the work done by the lift force was equal to the gravitation in the water? And so what if we take that net work a little different? What if we say it's net work equals the conservative plus the non-conservative? If net work equals 0, then these two works have to be equal, right? At least magnitude for sure. And so your non-conservative work would equal the conservative. I'm going to go magnitude here. Okay. And so if you recognize that change in mechanical energy is equal to the non-conservative work, and you recognize that it's equal to the conservative work, there's only one that's conservative. It's the work done by gravity. So that's why it felt maybe like you were backtracking to get the 2,300. We added 800, and then we ended up subtracting it, right? This is why. Is it always going to be this way? No. When do you have net work? When your object has constant speed, okay? Not all problems are going to have constant speed. Okay. Questions on the treasure chest? Let's throw a baseball. So later we'll do a basketball. Okay, we'll shoot it into the basket. Here we're just throwing a baseball straight up. It's going to come straight down. And that's going to sound familiar. Oh, Ms. Earhart, isn't this free fall? Can't we do old stuff? Why force us to do the new stuff? There are some benefits to work and energy. But at the end of the day, this one's going to talk about drag. We didn't do mathematical solving in kinematics with drag, okay? We did concept, but not the mathematics. And so this is where work and energy are going to come in handy. And so we've got a 0.1 kilogram baseball. It's being thrown straight up at 15 meters per second. And after 2 seconds, its vertical velocity is now -6. So let's kind of review free fall. It's going to go up, 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 up to a split second stop. And then it's going to come down, 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 down. And I'm going to put it right here as -6 meters per second. How do I know it doesn't return to the player's hand or hit the ground below? Free fall review. What if it did come back into the player's hand? Neglecting air resistance, it would be -15. Okay, there was nice symmetry with free fall, straight up, straight down. Okay, so being -6, partly due to the air resistance, trying to slow it down the whole time, but also probably hasn't reached the player's hand yet. And then it says how much total work? Total work, AKA how much net work has been done on the baseball. Well, work energy theorem, net work equals a change in what kind of energy changes? For 2 weeks, we said net work was equal to a change in kinetic. And so they gave us those speeds so that we can get and mass, so we can get the change in kinetic energy. And so we've got KE final minus KE initial. What's our newish equation for kinetic energy? One half mv squared. Now I'm running out of room, so I'm not going to, but since they gave us the mass, couldn't you factor out 1/2 m? Okay, as long as you know, don't say 6 minus 15 is 9 and let me square the 9. You want to take the difference of the squares. So I'm just going to leave it as is, just to save a little bit of room. And so the mass, 0.1. Final velocity, I'm just going to put a 6. Does kinetic energy really care about direction? Energy is scalar. Plus it'll square out, right? -6 squared is a +36. So mathematically it doesn't matter, but the concept of energy, it's scalar. It doesn't care if it's going up or down. We're just looking at the speed. And then minus 1/2 of 0.1 again. And the initial speed is 15. Don't forget to square. And so hopefully you see that it's going to turn out negative. And go on and get me that value. What is the change in kinetic energy? Hopefully we have a couple people calculating. Negative what? 9.45. And it should be joules. I didn't ask it, but kilograms is SI, meters per second is SI. So our answer should come out SI units. Okay. Everybody got 9.45? Okay. Negative, because what's happening? From launch to that 2-second interval, it has slowed down, right? It's moving 6, not 15. And so, yeah, you have a negative change in kinetic. B, what if drag, air resistance, what kind of force is air resistance? Conservative or non-conservative? Non-conservative. If it does this amount of work, negative 3.4 joules, negative because it's taking energy away from the system, right? How high is the baseball above its starting point? And so you may think, oh, I can solve for distance with kinematics, but we didn't take into account drag with kinematics. And so since it's a non-conservative work, I'm going to use that third version again. What kind of energy changes because of non-conservative works? Say it one more time. Mechanical energy. Okay. Or you could do a network approach. Okay. So side note, you could do network equals work done by conservative plus non-conservative. Both are going to get us the same thing. And so this change in mechanical, well, mechanical energy under normal circumstances, which I said these are normal circumstances, so we can include the Earth as part of our system. It would be changes in kinetic plus a change in potential energy. And no springs here, so it's just going to be the gravitational change. And I didn't draw a force diagram, but the only things working on it is gravity, which is going to be taken care of in the potential energy. The only non-conservative is going to be that drag. And so here's our drag piece. And so negative 3.4 equals, we already found the change in kinetic, negative 9.45, and plus the potential energy. And so we can actually solve for the change in potential energy by adding the negative 9 to the other side and get what? A positive 6.05? Now that's not our final answer. This is our energy, joules. They want to know how high. And so our equation for gravitational potential energy is what? M times G times that change in height. Delta H, delta Y. I try to use both. Okay, formula chart, delta Y. Now, lucky for us, our mass is what? 0.1. And gravity is 10. So it turns out our change in height is also going to be 6.05, but not joules. It would be meters. Okay. Now, just a clarification here. It says, how high is the baseball above its starting point? That's what we found. You would basically be assuming the starting point was your 0 meter mark. Okay. And so it's above your launch point. Okay. Yeah, there's still some distance from the maybe hand to the ground, but we don't care about that. It's just the height above the launch point. And that would be our final answer. Good deal? Okay. And just as a real quick on the other one, okay, it should go quicker now. Net work, this is, oh, that got loud, is your change in kinetic. And then the conservative work, just to reiterate, you would say it's equal to a negative change in potential. And then the non-conservative would be the work done by drag, okay? So you see, we'd be plugging in the same numbers and equations, you should get the same answer. But that negative, if you took the other approach, you would get a wrong answer in terms of sign if you didn't remember the conservative works have negative changes of potential energy. All right, page 5, basketball. A basketball player makes a jump shot. And you don't have to know what a jump shot is, but hopefully you know the spirit of basketball. Are we throwing this ball straight up? Is it coming straight down? Is that how you make a basket? No, there's going to be a little arch to it, okay? So just to compare it to the previous baseball problem, now it's going to travel some kind of horizontal distance. And so we've got this 0.7 kilogram ball. It's released from a height of 1.8 meters above the floor. So this is like an initial height. And it has a speed of 7 meters per second. And so if my basket is, you know, somewhere over here, and I'm not an artist, so there's my basket. So I have to give it some horizontal oomph. I got to give it some upward oomph. In other words, you're going to throw it at an angle. And so we know that 7 meters per second is the initial speed, is the initial velocity. Now they do not give us the angle. This is not going to be solved as a projectile. It is a projectile, but we're not going to do the whole XY chart. We're not going to find the components. Does energy care about those components? No, speed. You either have it or you don't. So this is the speed we'll use. And then it's going to go through the net. And so maybe our basketball is going to go through the net. And I'm going to do an angle, okay? Because if we do a perfect parabola, it would have an angle to it. And this is going to be our final location. They say it's 4 meters per second for a speed. And the net is 3.1 meters above the floor. Both distances are given above the floor. Read carefully, okay? What is the work done on the ball by air resistance? So don't neglect it. We're going to be looking at the work done by drag. And then should the ball be moving faster or slower than 7 when it again comes to, so let's keep it going. What would the velocity be if you return to that 1.8 meters above? Let's answer that one first. We can do this concept. How fast is it going when it once again is 1.8 meters above the ground? Okay, and so there's actually two answers here, okay? One is more correct today, but in the past, we said, oh, it's gonna be 7, it returns, right? If you neglect air resistance, the VF is 7. You see that nice symmetry. But with air resistance, VF is going to be what? Bigger or smaller than 7? Smaller. So it's going to be less than 7 meters per second. Because drag and air resistance is going to take energy out of the system. It's going to convert it. Okay, you could even go as far as to say that the air resistance is going to convert to some kind of heat, right? But it's going to be less than 7. So there's that question answered. Okay, now let's go back and find the work done by drag. Okay, drag is a non-conservative force. And so we're going to use that non-conservative work is equal to a change in mechanical energy. So that's the theorem. Now let's take it further. Mechanical energy is what under normal circumstances? What other energy adds to our mechanical, to make mechanical? Kinetic? Potential? Okay, so it's that change in kinetic plus change in gravitational potential. Do we have any springs yet? No, there's not going to be a lot of springs on today's examples, but we'll hit them next class, okay? And so each of these is going to be a final minus initial. And we could move the initials to the other side if you don't like 4 terms on the right-hand side. But they actually did, and I did that last period. I moved the initials, kind of made it a conservation statement approach. But then to solve for work done by the drag, I had to move them back to the right-hand side. So I'm just going to leave it where it is. It's already solved for what our answer should be. And so each kinetic energy, 1/2 mv squared. I'm using my subscripts. Potential energy due to gravity, mg hf minus mg hi. And so it looks really long, and on this problem, no one zeroes out. Can I cancel out mass? Can I cancel mass? I got a lot of masses there. Does it cancel out? No, why not? I'm solving for work, right? I don't want to cancel out mass when I'm solving for work. That wouldn't be a joule. Now, could you factor out mass from all of that? You could factor it out, say m times everything else left over, okay? But it's not required. So they did give us the mass, so I'm just going to keep it, okay? It might save you a little bit of time when calculating, but not tons. You know, if they were solving for mass, then I would definitely factor it out. And so 1/2, the mass of the basketball is 0.7 here. The final speed is when it goes through the net. They told us it's 4. Don't forget to square. And then minus the 1/2 of 0.7 again. Initial, they said it was 7 meters per second. Don't forget to square. And then mass again, times gravity 10. Final height, make sure you get final and initial in the right place. Final was at the basket, 3.1 meters. Minus 0.7 times 10. And the initial height is 1.8. So chances are, if you try and put this all in one calculator step, you'll miss a parentheses, you'll finger slip at some point. So me personally, I would either do 4 calculations or at least do the kinetics together, do the potentials together, okay? And so work this out. Drag should give us what sign of work? Should come out negative. We already addressed that previous with the blue. We said it's going to take energy from the system. And so our total finals should be less than our total initials. So work this out and let me know what you get. When you get an answer, let me know. 2.45. Okay, hopefully we all get that. And it should come out in joules because everybody was SI units, okay? Again, it's negative. Drag is going to take energy from the system. Good on that one? Okay. Then we're going to revisit a problem we've already done. We already did this roller coaster problem as a network equals change in kinetic. We're now going to do it from a non-conservative point of view. So it's going to get the same answer, boring on that regard, but we're going to use that third version that we just did of non-conservative work equal change in mechanical. So we got a roller coaster, 395 kilograms. It moves from point A, which is 5 meters above the ground. And so I'm just going to label that. So this is assuming the ground is 0. And to point B, which is 28. Maybe you remember me drawing the actual roller coaster. Last time we said, well, it was kind of a ramp, but they didn't give us the angle. And I showed you that you can just use the parallel gravitational force and vertical displacement to get our answer. And today I'm not even going to really address it. I'm going to use an energy approach. And so the chain, oh, and it moves up. Maybe tomorrow we go down. Up matters. And so now it tells us friction is going to do negative 20,000 joules of work. And the chain mechanism to help pull you up is going to do positive 30,000 joules of work. What is the change in kinetic energy? Well, both friction and the chain are non-conservative forces. And so what if we take this non-conservative approach? Now I'm going straight for the mechanical energy is kinetic plus potential, okay? Non-conservative would be the chain plus a negative, they told us, friction. Change in kinetic is actually what they say to solve for, so don't break it down into 1/2 mv squared. And then plus this change in potential energy, well, you can do final minus initial. The only thing changing is the height. And so similar, a little different than what we just did up above. I could just say it's mg delta h or delta y, whichever. And so using this version, not a net work necessarily, using the non-conservative version of the work energy theorem. And so the chain is going to do 30,000 minus 20,000. So on the left-hand side, we'll have 10,000. Change in kinetic, we'll keep. Mass, 395 times 10. And then the vertical displacement, you move from 5 to 28. Your vertical height change is what value? 23. And so whatever that comes out to be. And so our change in kinetic energy, when you get an answer, let me know. And those of you not calculating, what sign of our change in kinetic should we get? As you go up the roller coaster, 99% of the time, what happens to your speed? It slows down. So what kind of delta KE will we get? Should get negative. And those calculating, you should get negative. So let me know what you get when you get it. $80,850, and it should be joules. Everybody started SI units. By the way, back at textbook answers would probably just round that, sig fig, 81,000. This is fine. And you really got negative, yes? Okay, so it should come out as a negative change in KE. So it's a different way to solve the exact same problem we saw in the packet one, okay? And take your pick. I mean, you can do it either way. And then number 8, okay? We've got 5 ramps that lead to the ground, from the ground to the second floor of a workshop as shown. All 5 ramps have the same height, and B, C, D, E have the same length, but ramp A is longer. And the length they're talking about is the distance that the cart is actually going to travel. And so if I label those links, you know, A is longer, so I'm going to say L plus. And then B would just be L. C would be a total of L, and D and E, okay? So L plus, they didn't say it's twice as long, they didn't say, but it's going to be longer than the other links. Heights are all the same, they said. And so no difference on the heights. You need to push, you need to apply a force on a heavy cart to the second floor, and you can choose any one of the 5 ramps. Assuming no frictional force on the cart, thank you very much. We've got the wheels greased, maybe it's a very slick ramp, okay? Frictionless always makes our life easier, right? Rank the work you would do, so work done by applied, to move the cart from rest at the bottom, but also stopping at the top. And so each one of these ramps starts at 0 meters per second and ends at 0 meters per second. Not that you have to write it on all, but make sure you know that that's true. So really the only thing different other than actual shape, it looks like, is that length traveled by the cart. And so to get that work done by the applied force, wait, did they tell me anything about the applied force? Did they say you apply the same force on all ramps? No, they didn't tell me anything about the applied force. Now, distance would be that length equivalence, right? But I can't solve it with this equation. I don't know anything about the applied force. And so what's another way to find the work done by applied, which is a non-conservative? We're going to use that work energy theorem again. Non-conservative work equals changes in mechanical energy. And again, I broke mechanical down into its kinetic plus potential energy. Well, if you start at the bottom of the ramp at rest and you come to a stop at the top, what's your change in kinetic? Final minus initial, right? If both speeds are 0, what's the change? 0. That whole piece goes to 0. And so the work done by your applied force is going to equal that potential energy final minus potential energy initial. Well, they all start at the bottom of the ramp, right? So they start with 0 potential energy. Final potential energy is that mg final height, which was the same for everybody. And the cart that you're going to try to push on each ramp is going to be the same mass, okay? And so you'll get the same applied work on all ramps. And it doesn't feel right because you're like, oh, but some of those ramps you're going to have to push harder, right? Yes, the force applied might be different, okay? We saw that in the plan A. The one with more distance traveled, you don't have to push as much. But at the end of the day, the work done by the applied, by the person, is going to be the same on all these. Good deal? And that's assuming frictionless. Real life would have friction. Okay, I think we're going to do one more together, and then I'm going to have y'all small group several, okay? Page 6. We're going to do the top one. There's just something nitty-gritty different about it. And then y'all are going to try and finish this page before you leave, okay? So top of page 6, it says a 2.1 kilogram ball is attached to a ceiling by a 0.85 meter long string. So we're putting the string on the ceiling and we're hanging the ball down. And so if we start that picture, there's our ball. The string is 0.85 meters. Ceiling to the ball. The height of the room is 3 meters. So ceiling to floor is 3 meters. What is the gravitational potential energy of the ball relative to each of the following locations? So the moral of the story here, that ball is just going to hang there. No changes in kinetic, no changes in height. This one's getting nitty-gritty about that relative or the reference point. What do you choose as your reference point? Now we're going to do B first, because B first, the floor equaling your 0 meter mark, this is the norm. This is your standard, okay? Typically in any given problem, unless told otherwise, you can make the lowest point your 0 meter mark, okay? And so to find the gravitational potential energy, we're not changing, it's just what is it? mgh, okay? What's the height above the floor? 2.15. Okay? And so it would be the mass, 2.1 times 10 times 2.15. And we get what for the potential energy relative to the floor? Say it louder.
45.15.
Okay. And should come out in joules. So this is the energy from the floor. Now I'm going to go back to part A. A is atypical, but AP could so do it. Relative to the ceiling. What they're saying here is the ceiling is your 0 meter mark. The ball is below your 0 meter mark. So it's atypical, but to find the potential energy, mgh, it's the same mass, 2.1 times the same gravity, but now I'm below the 0 meter mark. So what would we plug in for the height from the ceiling? The vertical position from the ceiling? Negative 0.85. So again, this is atypical, but still possible. And here you're going to get a negative potential energy of what? What number do we get? It's like pulling teeth. Oh, come on. 17, we'll round it to 9. So 17.9 joules. And so we got a totally different number. We got a different sign. Did the ball do anything? No, it's just hanging there. Moral of the story, height is relative to whatever you say is your reference point, whatever they say their reference point is. Typically, it's the floor or your lowest point, okay? Earlier in the roller coaster, where we started out at A, which was 5 meters, we could have reset it and said, oh, that's 0. B would be 23 meters above that lowest point. And so your distances are relative to whatever that lowest point or defined reference point is. What if they define your lowest point, or what if they make your reference point the same elevation as the ball? Well, same type of deal, mgh, but what would your height be from yourself? If we're looking at the 0 meter mark as being where the ball is, I have no height above that location. And so it'd be 0. Height would be 0. And so the potential energy would be 0. But again, the ball hasn't done anything different. So it's all relative, okay? Just be careful. Most problems, B, the norm, the floor, your lowest point is 0, okay? But occasionally, they'll say relative to a different location. Good deal? All right, so y'all are gonna spend 10-ish minutes, okay, trying 10, 11, and 12, and I'm just gonna go in and help you. Number 10, there's 2 questions, but it's really the same thing. So it's really just one answer, okay, just FYI. It's one answer for both. So I'll give you that tip. And I don't think there's any other nitty-gritty differences. And so try these 10 minutes and then I'll, reveal the answers. Don't start with the key. The key is on Canvas. Don't start there. Give it a try. Use one of the work energy theorem statements. Try to solve it with one of those, okay?